Newtonian mechanics, again, except now we're going to throw in friction, tension, and fictitious forces. We're going to start by revisiting free body diagrams. We've got Pac-Man over here, and Pac-Man's pushing a block. And remember, when we draw a free body diagram, we draw the forces acting on something. So here I just drew the block as that red circle right here. That's the block. That's how physicists draw. And then every force that's acting on it. Gravity, normal force, Pac-Man, and then friction. So what do we do with this? Well, first we set up our coordinate system. It's always important to pick which way is up and which way is right, left. Then we start with Newton's second law, and we'll say F equals ma. But these are vectors. So we're going to break them up, and I'm only going to look at the x part right now. And I'll find out that FP, Pac-Man, pushes to the right, the positive x direction. Friction goes in the negative x direction, and this causes an acceleration of the block in the x direction. So force diagrams show the directions of forces acting on an object. Let's take a moment to look closer at friction. So if you push your hand on the table and move it around, you'll feel friction. Push down harder. What do you feel? Well, more friction. So what you're going to find out is that friction is proportional to the normal force. So this little fishy thing, that is proportional. And the normal force is how hard the surface has to push back against you. You push down harder, the surface has to push harder against you. And we call that coefficient of proportionality the coefficient of friction. Now we're going to talk about two. You may have noticed that it's easier to keep something moving than it is to get something moving. So if something is moving, you use this mu sub k, the coefficient of kinetic friction, and kinetic means moving. If it's not moving, you use static friction for when it's not moving, stasis, not moving. And it's very important to note that the force of static friction is less than or equal to. This is a little bit different, mu s sub n, because if you push something, it's not going to push you harder than you push it. Okay, you can't push on something and it's not going to, you're not going to push on the wall and the wall's not going to throw you backwards. Let's look at a couple examples. So in this example, we've got a block moving on a horizontal surface. We need to figure out what distance will it come to a stop. I need acceleration, which means you need Newton's second law. Now, Newton's second law, we're going to go ahead and split it up into an y parts and the x part. Now, the reason we're looking at the y part is because we care about this force normal, because friction is equal to mu sub n. So if we take this, let's start with the y's. We have normal force up, force due to gravity pulling down. That's what this negative means. That negative is down. And then it just becomes your normal force is the force of gravity, or mg. All right, that's good. What do we do with this? Let's look in the x direction. So our force in the x direction is negative friction, which we know is mu k sub n. Oh, wait, we just solved for m. Let's put that over here. And there it goes. Oh, those m's are going to cancel out, and you're going to get the acceleration is just negative 1.57 meters per second. And negative is just directional. It means to the left in this case. Now go kinematics. We're going to start this by looking at everything we know, just like you always start anything. Right? We know that delta x is equal to xf minus x initial. Well, x initial is just 0, so that's going to go away. It stops, so v final 0. And let's just rearrange. So I rearrange. I'm going to solve for this x final. Again, x initial is 0. V final is 0. Use our numbers that we got from the beginning, including the acceleration that we solved for using Newton's second law. And you will get that that box is going to travel 5.09 meters. That's pretty far. Now let's talk about tension. All tension is just a force from cables or ropes. The important thing to know is that tension always goes along the rope, and it's always going to pull. You can't push things with a rope. It's really hard. I will mark it with the symbol T because I'm not that creative. Now let's move on to something a little more interesting. And that something's going to be weight. So all weight is the force that gravity exerts on an object. So on Earth, this is mg. However, keep in mind that if you're not on Earth, it's g mass of the planet over r squared, just using the derivative of the potential energy, like we've done. But let's talk about apparent weight. Here's where it gets neat. So this is a measure of the normal force. Just imagine, if you weren't standing on the Earth, like if there was nothing under you, you would have no idea what you actually weighed. So when we weigh things, like if you're standing on a spring scale, you're actually measuring how hard the springs are pushing against you. And they push as hard on you as you push on them, so it comes out equal to your weight. But what if you're accelerating? Like this example. That's a good thing we picked it. So here we're accelerating 70 kilogram person. Again, always important to know which way up is. And I will talk about the force. So here there's only two forces, the normal force and then gravity. However, it is accelerating. So again, sub in normal force up. Gravity is pulling negative y in this case. Solve for the normal force. And I get 70 kilograms, because that's what MAY is, minus 2. Oh, sorry, AY right here. And then 70 kilograms times G. Oh, wait. This is less than the person, because they're accelerating downward. So the normal force isn't pushing as hard on them, therefore they feel like they weigh less. Which also is why when an elevator starts, if you're moving down, you feel that little jerk in your insides. Pretty neat. So how far would you have to fall? How fast would you have to accelerate downward to feel weightless? Well, let's try it out. All right, so I want no normal force. That would be the condition for weightless. Wait, let's cancel out those m's. Oh, if I accelerate downward at negative g, negative the acceleration of gravity, I feel weightless. I just need to be in free fall. And that's what happens inside space shuttles, or if you've ever been on a carnival ride where they just drop you. If you're in free fall, you feel weightless. And now something a little different, fictitious forces. All of fictitious forces, it appears when you are in an accelerating reference frame. That's it. Remember Newton's law works in inertial reference frames? If it accelerates, you get weird stuff. So let's find out. We'll separate the acceleration of a person to Earth. And this person's riding an elevator, to the elevator in the Earth. So let's look at the acceleration of the person in the elevator, in this case. So the acceleration of the person in the elevator is just person on Earth minus their acceleration of the elevator relative to the Earth. Relativity, back to stuff we talked about earlier in the semester. You remember that. Well, the acceleration of the person in the Earth is caused by the force of gravity, but then you have this thing. Who knows where that's acceleration coming from? What force is causing it? I don't know, and you can't ascribe it to anything. The only thing that it can be is that your reference frame's accelerating. So that's why they call it a fictitious force. If you're in an accelerating reference frame, you see it, but you can't attribute it to anything other than, your moving reference frame, a non-inertial reference frame. I should be more specific. I hope that helps, and I will see you in class.